Can you explain to me the meaning of energy from the vacuum? I don't want to make it imply that I am endorsing this particular concept.
But that will not be what you're saying.
But I don't want it to be implied that I do that.
Right.
Yeah. Okay.
And we just want to talk about phenomenology and experimentation.
Yeah. Okay.
Yeah. No, we're not looking for your endorsement.
Yeah.
We're just exploring.
Okay. Fine. Okay. I've been in the field of material science for 30 years. I was educated first at California Institute of Technology, where I first got introduced into the subject of material science. However, actually at that time, my major was more in electrical engineering. But through research, I got very much interested in material science because it is so rich in science at the same time as practical, and I like that combination. So after graduation from California Institute of Technology, I moved on to Massachusetts Institute of Technology, or MIT, for my graduate work. And there, my focus was on material science. And in MIT, I got involved with carbon research for the first time. And that has been the focus of my research for the last 30 years. Carbon, referring to graphite, carbon fibers, carbon fiber composites, activated carbon, diamond, nanotubes, quite a large variety of materials, and a lot of applications involved. And I have been working on a large variety of properties of these various materials. Not only the structural properties, but the functional properties, such as the electrical properties, how the electrical and the mechanical properties connect to one another, and also the properties related to electromagnetic fields and thermal applications. And carbon fibers are most important from a practical point of view because of the carbon fiber polymer matrix composites. The polymer matrix primarily epoxy. And that's, this is an example of the carbon fiber. It looks like hair, but it's just a very small fraction of the size of our hair. And it's all carbon. And it is very strong and stiff in this direction, but it's very light. And so it is very effective as a reinforcement. So one can embed these continuous fibers in a certain matrix, such as a polymer matrix, and after curing or letting the polymer solidify, one obtain a stiff composite like this. And this is what's widely used for aircraft structures because of their combination of lightweight, high strength, and high stiffness. And compared to steel, for instance, it is much, much lighter. And so for fuel saving in particular, this is very much used for aircraft, and nowadays they are getting to be used more and more for automobiles as well. And also for tennis rackets and fishing rods. And so the structural side has been the prime application. However, because of my background in electrical side, I have been looking at the electrical behavior of this material, something which is kind of not ordinary, because for structural material, people don't usually look at the electrical side. And by looking at the electrical side, I have been able to observe some very interesting phenomena. And in the electrical side, the behavior depends on the direction, because as you can see, the fibers are oriented. Okay, it's directional. So if you make a composite, then if, let's say, the fibers are lined up in this way, then the properties of this composite would be very different in the different directions. Not only are they different between this direction and that direction, they are also very different in the vertical direction. Because a laminate is really a stack of the fiber layers. Each fiber layer consists of thousands of fibers thick along the thickness of that fiber layer. And each fiber layer is called a ply or lamina. And you have all these plies stacked up, and then you consolidate them together under heat and pressure usually. Then one obtain a composite. And this is the vertical direction, what we call through thickness direction. And it is the electrical behavior of this through thickness direction which I have investigated a lot in, and that's the direction which has received very little prior attention, because that's the direction perpendicular to the fiber layers. And I found this direction's electrical behavior to be very interesting. And the reason why this direction is interesting is that the electrical conduction in this direction hinges on the degree of touching between the fibers of one ply and the fibers of the next door ply. Okay? And one can control the extent of that touching by the fabrication condition of this laminate. For instance, by the curing pressure, heat and pressure, I said. Okay? So that pressure, so-called curing pressure, which is the pressure applied during the curing or the making of the composite, can greatly affect the extent of fiber-fiber contact between the fibers of one ply and the fibers of the next door ply. And because of that, the electrical conductivity in the through thickness direction can be much affected by the way this laminate is made. Okay. All right, so I have made a study of the electrical conduction behavior in this direction for different types of such laminate, these different types being different in the curing pressure. Okay? And so these different types are different in the extent of fiber-fiber contact across the layers. And I found different behavior, systematic differences. That is how the conduction behavior correlates with the curing pressure. There is a very consistent correlation. So in order to study the electrical conduction behavior in the through thickness direction of the composite, that is in this direction, we take two plies, okay, and we made the plies so that we lay one on top of the other. So this is the top lamina or top ply. This is the bottom lamina or bottom lamina or bottom ply, 90 degrees, one over the other. Okay, and this is the junction, and we consolidate this junction. That is, make a composite out, a two-ply composite out of this junction, by applying heat and pressure. The pressure being the pressure in this direction perpendicular to the sheet of paper. And now the reason why we want to make it in this configuration is that these fiber groups sticking out act as electrical leads. So in this way we are able to get current passing through this junction and measure the voltage across that junction. Just simply using these as electrical leads. Okay, and there are 4 electrical leads, which turn out to be very useful because we can use 2 of the leads, A and C in this case, for passing current, and use the other 2 leads, namely B and D, for measuring voltage. Okay. The current thus goes along this top layer, along this leg, and then it goes down in the direction perpendicular to the sheet of paper from the top layer to the bottom layer. And then it goes on along this leg of the bottom layer. Okay, so that's the current path. Now the carbon fibers are much, much more conductive than the polymer. In fact, the polymer can be considered to be electrically insulating. Okay, so for this current path, the major resistance is the resistance across the junction. Okay, and then the voltage is measured across B and D, and an ideal voltmeter has no current going through it, and so we can just assume no current going through these two legs, and because of there being no current, then the potential at B is essentially the same as the potential at the top of the junction, and the potential at D is essentially the same as the potential at the bottom of the junction. Okay, so in this way, the voltage difference between B and D gives the voltage across the junction, and the voltage divided by the current gives the resistance. Okay, and this resistance reflects the contact resistance, which is the resistance across this interface. And this contact resistance multiplied by this junction's area, what's called the contact area, gives the contact resistivity, which is a geometry independent parameter that describes the nature of this interface.
I have a quick question.
Mm-hmm.
The common interface area, and I may have missed it. Is there pressure applied to this, or is there glue, epoxy? I mean, or is it just laid on each?
Yeah, just laid on. Now, the epoxy is already surrounding the fibers. Okay. That is, right. Each lamina already has the resin, right. Tacky resin. Right. So you lay these two tacky strips one on top of the other, and then through hot pressing, okay. The epoxy would cure, and then it would stick together. So actually, this is ordinary way of making these laminates.
So the pressure is applied during the curing process?
Only during curing, yes. After it's finished, the making process is finished, then the heat and pressure are removed. Okay, thank you. Okay. So we have here a sample, an actual sample of that thing. This is the bottom lamina, and this is the top lamina on top of it, and this is where they touch, and this is the junction. And we are interested in the contact resistance of this junction. That is the resistance in the direction perpendicular to this piece of paper. And we pass current from here to here, so that the current goes here and then down the junction from the top to the bottom layer, and then along this leg of the bottom layer. And while doing that, we measure the voltage between these two legs. Okay. Now, this sample exhibits the conventional behavior, namely, as you increase apply a positive current, and as you increase the current, the voltage is positive and becomes higher and higher. Okay, and this is the ordinary effect. In fact, the current and voltage are linearly related to one another, and it's positive slope. The current-voltage relationship is positive in slope, and this is the classical positive resistance situation, and this applies for the case of the curing pressure being rather small, so that the extent of touching across the layers is not very high.
When you talk of the curing pressure being comparatively small, what orders of what range are you talking about here?
Yes, the curing pressure, this is from my paper.
Yeah.
So this is curing pressure in megapascal. And 0.13 megapascal is considered a low curing pressure. 1.4 megapascal is considered a high curing pressure. So even high is actually not a very high pressure. 1 megapascal is the same as 145 psi. So it's not very high pressure, but just on a relative scale. And so using a relatively low curing pressure, one attains the conventional behavior, positive resistance. And we're going to demonstrate that experiment right here. Okay, and Dr. Wang, who is the first author of that paper, is with me, and he's going to help me with this demonstration. It's all automated, so it's going to come out. Now he's going to crank up the current, and the voltage, is all automatically current voltage automatically collected and it's going to be displayed. So let's put the display up on the computer. No, just wait. Now he's cranking up. So the top curve is the current, the bottom curve is the voltage, and he's cranking up the two. It's just manual cranking, so it's not very smooth. Nevertheless, one can plot the current versus voltage, and you see it's linear, positive slope.
Which is a completely standard,
Yes. Yeah.
generic current voltage relationship.
Yes. All right.
And this is with material that has been cured at what pressure?
The relatively low pressure, which is around this 0.13 megapascal area.
Okay, so this is generic carbon composite cured material.
Well, all these are generic, just
Okay.
that I vary the curing pressure.
Exactly.
Yeah. All right. So now we proceed to the another such sample, but made with a relatively high curing pressure.
We're changing samples now.
Now, yes, we are changing sample. Okay, so this is the second sample, one which was made using the relatively high curing pressure. And we do exactly the same experiment, passing the current like this and measuring the voltage across these two legs. So let's do that now. All right, so he's cranking up the current manually again. And the top curve is the current, the bottom curve is the voltage. And you can see that while the current is cranked up, the voltage goes down, it goes negative. And so now you plot the current versus voltage. It is a straight line of negative slope. Okay, and this is what we call apparent negative resistance. Okay, now first of all, I'd like to explain that I don't think that this is true negative resistance. That's why I call it apparent negative resistance. And I believe that this phenomenon has to do with the electron flow having a backflow. That is, you have current or electrons going from one layer to the next layer. Okay, and then there is a tendency for the electrons to flow backward. Okay, from the one layer back to the first layer. And this backflow is driven by entropy. Okay, just like diffusion is driven by entropy. And because of this entropy-driven backflow, you have this backward current. And under certain situations, this backflow can appear to dominate. When that happens, you have the apparent negative resistance. Okay? So I call it apparent because I believe that it's entropy driven. Okay? true negative resistance, which I'm not claiming, would have been driven by energy rather than driven by entropy. Okay? That is, if it were true negative resistance, a negative charge would go toward not the positive end of a voltage gradient, but a negative end. That would be true negative resistance. And that's driven by energy. Okay? But in this case, it's not driven by energy. I believe it's driven by entropy. Okay? And that entropy causes the tendency for backflow, and that backflow in turn results in the apparent negative resistance. Okay.
What led you to look at this particular set of parameters with these materials? What inspired you to look at the voltage and current characteristics? Or is this something that's particular to your field of work? As you had said, you focus on the electrical characteristics of the composites.
Yeah, that's a good question. I'm interested in the electrical side of a structural material, seemingly an odd thing. The reason for that is that I'm interested in making smart composites, or multifunctional composites. I want to use the electrical behavior as an output or indicator, so that the structural material becomes a sensor. Okay. So it could be a sensor of damage, sensor of deformation, sensor of temperature, whatnot. Making use of the structural material itself as the sensor is attractive compared to the embedding of a sensor into a structure. Because if you embed, it's like having a hole in the structure, and the mechanical properties of the structure would diminish. And also, it's hard to repair, once it's embedded. And the cost is high for a device compared to the structural material itself. And also, if you embed, this sensing ability is only here and there, not everywhere. Okay? So that's my motivation, the development of multifunctional structural materials. Okay. There could be some applications in the area of, again, multifunctional composite materials, making use of this phenomenon to engineer certain electromagnetic or magnetic properties that are particular to these structural composites. But from a scientific point of view, I think that the most interesting aspect is that one can tailor a material to give very different such conductive behavior. Okay? In fact, I can tailor it to make it more positive, or that is, there's different gradations of positive resistance and apparent negative resistance. We can tailor it to different degrees through the curing pressure, for instance. And this tailoring of a material to give whatever electrical conduction behavior that's desired is, I think, the most intriguing part of it scientifically.
This has been patented, hasn't it?
No, this has not been
It's not been
patented.
patented.
Mhm.
Might I ask why? Normally one expects everything to be patented. So
Yeah, well, the patenting procedure is something that relates to the university filing patents. It's not just me.
yeah.
Okay, and patenting was not pursued.
All right.
Mhm.
And this is the, you presented these results originally in, I think, 1998, was it, at a symposium in Las Vegas?
Yes.
Yeah. And this is the process that you were talking about at that point in time?
Yes, yes.
Yeah. And I guess you're saying essentially this is in the public domain now?
Yes.
So, okay. So there's no question that I mean, if one wanted to pursue this, say with additional research, you wouldn't have to get the university's permission to use it, or I mean, it's not protected by patent or anything.
Right,
so
right.
Anybody can use it for
Yeah,
anything.
that's right.
Okay.
Yeah.
I'm just trying to recall. There was the university at one point in time, I think, was going to license it, weren't they? Or I'm on the wrong track here.
Well, the university at one point was considering getting patent protection,
Okay.
but it was eventually dropped.
Okay.
Yeah.
Do you have any, is there any extended further, is this an isolated phenomenological discovery, or is there something you have ideas about extending this into other applications, other areas of investigation, now that you know that pressure variances affect the apparent negative resistance? Do you have any ideas about taking that another step into other areas or other uses or methods of applying this situation?
One can extend this experimentation to composites with matrices other than polymers. And I've done some work with cement as the matrix. And a similar behavior exists there.
By the way, when you say cement, you mean glue, as we would commonly.
No, cement like concrete.
Oh, really? Real I
Yes,
see. Okay.
yes.
Oh, very interesting. Oh,
Uh-huh.
ah.
I think one simplest application is just to use this as an electrical device. An electrical device that exhibits this particular current voltage characteristic.
It is what it is.
Yes, it is what it is, and just use it as an electrical device. We can tailor it, and so you have a series of electrical devices.
Have you had inquiries in that regard? People interested in replicating it for application as an electrical device? Have people inquired to you about that at all?
Not a whole lot. Yeah.
Okay. Thank you very much.
Okay.
Very good. Very well done.
Good.
Yeah, that's
Thank
correct. That was,
you. Okay.
And you look good too.
yeah.
And you look nice.
Oh, thank
Yeah,
you.
you're great.
Thank you.
Are you familiar with Chung's work?
Yes, the negative resistor that she built is absolutely for real. Now, as far as I can see, somebody's put a clamp on that. Because they filed the patent, and everything like that went fine. But all of a sudden, you notice a great silence, which means somebody is using it for some kind of classified project. That's what it means. In my view, having been there in aerospace and know how they work, the work was being funded, as I understand, probably by agencies that would, in fact, do that.
So at age 18, I came all by myself to America to study. And I went to California Institute of Technology, or Caltech. And it just turned out that I was one of the 4 first women graduates of that university. That's my husband of 30 years.